Hi everyone, today we're going to be talking about yaw angles and why the yaw angle gets smaller as you increase the forward speed. We're just going to use a really simple picture of a bike here, or just do a rectangle. The bike is going in this direction, which means that the bike actually sees wind coming from this direction. We're going to call this velocity. Let's say we have a crosswind which is coming at 90 degrees. And that's going to be CW for crosswind. So the bike sees a combination of this and this in the form of a vector that looks like that. We'll call that V effective. So the wind the bike sees is actually this V effective. And our yaw angle is the angle between V effective and the direction of travel. Okay, so let's just do a really super simple example where we're going to have a crosswind which is constant for two cases. We'll say this is 10 kilometers an hour, and we'll do the same here. Now vectors have magnitude and direction, which means I can visually represent this problem. Let's use an arrow which is about the same size as this this crosswind one here, and we'll say that this is a forward speed of 10 kilometers an hour. So our V effective is going to look like this. Yeah, and this yaw angle here is going to be big. Now let's look at something which is 50 kilometers an hour. So if I draw this original vector here 5 times longer than the one I've drawn there, that's going to represent 50 kilometers an hour. 50 kilometers an hour. And remember, this one here is the same 10 kilometers an hour. So our V effective is going to look like this. So visually, we can already see that this angle theta is a lot smaller than for this case. And that's essentially what it is. So as you increase your forward speed, assuming a constant crosswind, the length of this vector is going to get bigger and bigger and bigger. And then that is going to make this angle get smaller and smaller and smaller. That's essentially what it is. So if we visually represent this on a graph, we'll have here the velocity, which is the forward speed, the theta angle, which is the yaw angle. It'll look something like this. It's not linear because on a right angle triangle, which we saw before, you have A and B, and we have this angle here where theta is equal to the inverse of tan A on B. So as we increase the velocity here, you can see that this becomes increasingly smaller. At large ratios of A on B, let's say A on B equals 1, let's say that's here, then your theta will be 45 degrees. And if you get down to something like a ratio of 10 here, which would be the equivalent of 100 kilometers an hour forwards and a 10 kilometer an hour crosswind, we're looking at a theta angle of about 5 to 6 degrees. So you can see how quickly that changes, and that's essentially the relationship of yaw and forward speed.